Espérame.
Sí, voy a hablar. Aquí hablo. Good morning, everyone. It is a great pleasure and honor for us to welcome Professor Rigoberto Advincula to CIMAF today. We would like to express our deepest gratitude for accepting our invitation to deliver the talk Artificial Intelligence, Machine Learning, Directed Polymer Synthesis, and 3D Digital Fabrication. Professor Advincula's presence is truly a privilege, and we are confident that his visit will help strengthen our links with the University of Tennessee and their macromolecular science group at Oak Ridge National Laboratory. We also want to thank all attendees, both those who are physically present and those joining us virtually through CIMAP social media channels. Now, I invite Dr. Bonilla to present a brief curriculum vitae. After this, curriculum vitae Professor Advincula. After this, we will then have the opportunity to enjoy a seminar that will provide a deep and up-to-date insight into polymer synthesis and 3D digital fabrication driven by the most advanced technologies. Thank you all for your attention and welcome. Thank you.
Okay. Thank you everyone for being here. I have the honor to introducing a very passionate and esteemed worldwide influential scientist in polymer science, but overall introduce a very good friend. Rigoberto Advincula is a governor chair professor in Oak Ridge National Lab at the University of Tennessee and belongs to the Department of Chemical and Biomolecular Engineering. He's also a group leader at the Center of Nanophase Material Science, CNMS, in Oak Ridge National Lab. His area of expertise is in organic and polymer chemistry, nanomaterials, flow chemistry and reaction engineering, additive manufacturing, and biomaterials. He has led major projects including a machine learning, flow chemistry lab, and Oak Ridge, and advanced nanocomposites manufacturing with DOE. He's a fellow in different scientific societies, including the National Academy of Inventors, the American Chemical Society, ACS, the Polymer Science and Engineering Division from the ACS, Polymer Chemistry Division, ACS, the Royal Society of Chemistry, and NECH and NATAS, North American Thermal Analysis Society, and also a distinguished member and friend of the Mexican Polymer Society. Since the first binational meeting organized by SPM and Polymer Division for the ACS in 2008 in Los Cabos. He has been appointed to the World Economic Forum, Advanced Materials Council. He has held several visiting professor positions, including Waseda University in Japan and the Max Planck Institute for Polymer Research in Germany. He obtained his PhD in chemistry at the University of Florida and had postdoctoral position in the MPI of Stanford University. He is a passionate and mentoring student and establishes interdisciplinary STM programs. His fruitful and influential scientific work with 22,000 citations and skills factor around 81 has made him worthy of several international honors and recognitions. Dear students and esteemed colleagues, I give you Professor Advincula.
Muchas gracias, José. Buenos días, buenas tardes a todas las localizaciones de CIMAP. Soy filipino originalmente. Muchas cosas similar, between Philippines and Mexico. because of the Spanish heritage and the galleon trade via Acapulco. So long time ago. Anyway, yes, I am happy to be here in CIMAB in Mexico. I have been a friend of the Mexican Polymer Society, SPM, Sociedad Polimérico de Mexico, for a long time. So we have organized many conferences together with the American Chemical Society Polymer Division. And more recently, we have had a big conference in Puerto Vallarta with the Pacific Polymer Federation, or PPF, to which Jose and I were co-president last year. So it is really, for me to visit Mexico is like visiting home. Okay, so thank you very much for the warm reception. And I'd like to then proceed with the lecture. And so hopefully this should be seen on the screen. There you go. Okay. All right. So to start my lecture, I am with the University of Tennessee as a professor, but I'm also a group leader of the polymer group at the Center for Nanomaterials Sciences at Oak Ridge National Lab. And before this, I was professor at Case Western Reserve University. And I'll put the context why this is an important connection.
Nosotros vemos la vista de edición. Si pudieran, por favor, cambiarle a la vista completa.
Gracias. So at Oak Ridge National Laboratory, this is the Center for Nanophase Material Sciences next to the spallation neutron source. This is a $10 billion facility by the US Department of Energy. My office and the laboratory that I had is located actually in this floor. And this facility houses the neutron scattering setup, which is very important for materials research, biological sciences, because of the neutron sources to do many types of in-operando experiments, reflectometry, echo spin, and so on. But at the university, I'm also part of the Institute for Advanced Materials and Manufacturing, which I have a laboratory mostly composed of graduate students as well as postdocs and undergrads. And a little picture about the city of Knoxville. It is where the University of Tennessee has its flagship university. And in a very busy season, it is colored orange. In fact, the pride of the university this week is they won the national championship for baseball for the collegiate level. Okay, so in the university, most of my students and postdocs are where we do most of our mentoring and work related to 3D printing and materials research. And here are some of the cover journals of what we have prioritized through the years, which is mainly nanostructured materials, polymer materials, surface characterization, sensors, and different types of soft matter studies. So at Oak Ridge National Lab, I had the macromolecular nanomaterials group where we do a lot of synthesis of polymers, deuteration, state-of-the-art characterization, simulation, and when I moved to the lab, I established there a 3D printing facility for research and materials development, as well as leading some of the effort on AI and machine learning driven flow chemistry and polymer synthesis. And it is one of those user facilities who's actually open to collaboration or access. Meaning, if you have a proposal that gets funded, it's free. And you can have collaborations from the US and also from abroad. And I'm in charge basically of the polymer group in this operation. May have to do this manually. Now, a little plug-in. I am the editor-in-chief of MRS Communications. So I welcome your best contribution, research letters, review articles, methods letters, and other types of journal peer-reviewed as well with materials research. And this is published together with Materials Research Society and Springer Nature. And by the way, we are very active, or I am, Jose and Tanya are very active with the IMRS in Cancun, where we have every year a symposium on additive manufacturing. So before I go further, let me describe to you my evolution in research and also where you can assess your current interest and progress in research. You see, the scientist Niels Bohr is very famous because of his contribution to quantum physics, or basically the atom theory. On the other hand, some of you know Edison, who invented many things and actually established General Electric as a company. And he was famous for saying that invention basically is 1% inspiration and 99% perspiration. So where is a scientist going to position himself? Well, many years ago, my interest was more of basic research, but these days I'm more like a pasture, or this is what we call the pasture quadrant. Some of you may or may not have heard of pasture, but if this morning you drank some leche, some milk, pasteurized milk, or if you're in the laboratory, you're pipetting pasture pipette, okay? Or in organic chemistry, he's of course famous for symmetry and also chirality, okay? So he's a scientist who not only contributed to the basic science or fundamental science, but he did a lot of help and contribution to society. So these days, I find myself doing more things related to pasture. And whether you do it in a national lab or a university, you have opportunity to contribute to society. Or at a certain point in your career, you want to do more science, okay? Or you really just want to invent and file patent after patent after patent. Nothing wrong with that. But you pick your battle. So it's because the science of today is the technology of tomorrow. And you probably would have heard this in many forms, but this is how things go. Now, let's talk more about polymers. You see, polymers are big molecules. We sometimes just call them macromolecules, or some of you use the word plastic. Well, as a macromolecule, it has many properties related to the chain length, the composition, the microstructure. Many fundamental properties have been investigated and very dependent essentially on synthesis. In fact, as I'll describe to you, our journey on macromolecular synthesis has allowed us to build what we call structure, composition, processing, and property relationships. And as you can see here, a lot of science can be done on polymers in terms of the microstructure, composition, and eventually the properties. On the other hand, polymers are also true nanomaterials, because polymers can be arranged in a surface, can be grown like a hair, a polymer brush, or it can be observed as a complex in a colloidal particle or complexation with proteins. Either way, we have dimensions that rival carbon nanotubes, graphene, quantum dots, gold nanoparticles, meaning they can be of the order of a few nanometers. Now, a particular attention we did many years ago was to focus on the interface. This interface can be structured based on chemical adsorption or physical adsorption. It was very important for us to know how to order them layer by layer, or to grow the polymer with very high density, or even use electropatterning or electrochemistry to produce different types of useful devices. And so the journey began with a lot of interest on synthesis. So for example, early in our group, we focus a lot on polymers that are able to do electron transfer or charge transfer, or simply fluorescent. And these materials have found their way in organic light-emitting diodes, in solar cell devices, sensors, where it's very important to focus not only on the pi delocalization, but the whole or electron mobility. On the other hand, we pioneered a lot of work related to hybrid nanomaterials, where we will take a quantum dot or a gold nanoparticle, surround it with dendrons or dendrimer complexes, and we are able to control the charge transfer, electron transfer, or even uses of these materials as part of biomarkers in biomaterials. The next interest we had is on what we call supramolecular chemistry based on high polymers. The way we did this is to look at organic chemistry as a way to design templates where we can control the entanglement, the catenation, or multi-polycycles. And we can start, let's say, with a complex with phenanthroline or different types of guest host systems. And then, based on mathematical knot theory, for example, produce a triple knot. And this type of work involves a lot of planning, design, and even programming of the synthesis approach. Another interest we had was on functionalization of surfaces. So this was done by doing what we call surface-initiated polymerization, where we will attach macro initiators or self-assembled monolayers of initiators on surfaces or particles, and then control the polymer brush density, the swelling regime, and composition. Yet another work we started back then in the late 90s was to focus on polyelectrolyte complexation, where you can have a simple charge pairing of a negative or positively charged polyelectrolyte, and then you can form layer by layer assemblies or hollow shell complexes, as shown here, where you can have applications related to drug delivery. These days, actually, we use a lot of polymer electrolyte complexes for 3D printing. I've also trained many students who focus on biomaterials or biomedical engineering research. In this way, we can control the proliferation of osteoblasts or fibroblast cells, or look at the differentiation of mesenchymal cells, or look at the use of DNA for sensing, as well as various surface-sensitive techniques like the surface plasmon resonance spectroscopy to build sensors. Actually, many types of platform we develop by combining surface plasmon resonance spectroscopy, which is a type of surface wave guiding, or the generation of what we call surface plasmon polaritons and gold. And we combined it with electrochemistry to produce sensors and different types of surface-sensitive probes. And then lastly, before I go to 3D printing, some of our work involved collaboration with the Steinmetz group back at Case Western Reserve University, where we look at viral polymer and polymer drug delivery constructs based on the plant virus. So no, this is not the COVID virus. This is not harmful viruses based on what we call cowpea mosaic viruses. But as you can see, they form beautiful structures, very symmetrical, and we can functionalize them, let's say, for applications in photodynamic therapy. So what I've shown you really are some of our interests that involve more fundamentally. Now, in processing strategies, and again, I would cite my time at Case Western Reserve University, we worked with a center which was able to produce multi-layer constructs by essentially extrusion of melt or melt plastic, where let's say we can combine polystyrene and PMMA, which are two different polymers in terms of their chi interaction parameter. And then we will use multipliers that eventually allow us to make very exact multi-layer film structures, sometimes to the order of 10 nanometer in thickness. And actually, when you reach 10 nanometers, PS, PMMA are indistinguishable. So that type of artificial processing is what we call the CLIPS process. It's still very much in place, where we did a lot of work related to the chemistry of these multi-layer constructs, whether it's the use of guest host systems to demonstrate drug release by dissolving one layer, or we can use this as scaffolds for tissue engineering. We have used this also for patterning of polymer brushes. And then lastly, we have demonstrated the use of colloidal constructs based on lithographic and non-lithographic features on these multi-layer films. And as you can see here, the distinguishing element is we have this cube, but then this cube also has a lot of internal multi-layer structures that are very highly ordered. So I have shown you basically our research interests prior to 3D printing. So how did I end up with 3D printing? Well, it started really about 2014 when I looked at the space of other processing and exciting materials direction that we can involve more engineering approaches and even digital manufacturing. But actually in 2016, I was invited at the World Economic Forum in Dubai. So I'm a member of the World Economic Forum Advanced Materials Council. I did not go to Switzerland. That's only for rich people. Okay. So they had to send me to Dubai, but it's not bad because they treated me with a really red carpet treatment. But as you can see here, when I gave this talk, I emphasize on inner space, outer space, application to robotics, bio-inspired design, tissue engineering, and maybe in the future, you can do 3D printing to have the moon base using moon sand or moon regolith particles. And I'm happy to say that this was 2016. It's about 8 years already. And really, half of what I gave in this talk have come to fruition. So this is really how fast this field has advanced. And materials research is key to a lot of these developments. Now, these days, you can buy your own 3D printer, maybe from Amazon, okay? I don't, Temu, maybe Amazon, Temu, or Lazada, whatever. But it's not very expensive, okay? And you can play around with plastic or different types of resin materials, and it's actually very cheap. But if you want a massive parallel printing or printing farm or big area additive manufacturing, it is possible. It is the fastest growing manufacturing method that is tied to AI, machine learning, digital manufacturing, and sometimes they just say Industry 4.0. Okay, so you have to get into this, I believe, even as a polymer chemist, because you either can use it to repair things in your laboratory to make different types of sample holders, or you can develop new materials for research. So what fascinates me is that you can borrow from nature. So bio-inspired design, biomimicry means you can get the digital design. Yes, you can do that using PET scan or MRI. And you can digitize that. You can convert it to an STL file and start 3D printing. So for example, here you can see some natural structures or symmetry that can be reproduced in plastic. In fact, this chair, the design itself was borrowed from the shell of a mollusk because of the nacre structure. And this has some very interesting mechanics because it's flexible, durable, but it's also beautiful. Now, in the biomedical space, this is a big industry now. In the area of dental application, bone implant, regenerative medicine, this means that you can have different polymers that can be useful and are biocompatible. On the other hand, the replacement of bone with polyether ether ketone can really be done simply by 3D printing different types of infill volumes or design, where you can change the mechanical load of the bone function different from the face compared to your femur or heavy load design. Another, which Oak Ridge pioneered a lot, is in the applications for the automotive industry, big area additive manufacturing, meaning this application has gone into different types of mainstream manufacturing. So for example, the first 3D printed sports car, this Shelby Cobra with a design based on a 1964 production, was made in record time, less than 6 months, using 3D printing. And as you can see here, several concept designs or even parts used for aerospace or engine parts can be done by 3D printing. One of the emerging fields in the area of 3D printing is application to soft robotics. This means that instead of your traditional mechanical gears or implements based on metal, you can use hydraulic, pneumatic that will require elastomeric or rubbery materials that you can activate or actuate based on this movement that can be designed using inspiration even from nature. So actually, there's a term that is coined 4D printing. 4D printing is where you combine the material properties, the stimuli responsive properties of a material, and the geometrical design of 3D printing. In stimuli responsive materials like activation with heat, light, okay, or chemical response, you have a change on the property. But if you combine that stimuli response with the geometric design, you can come up with origami, karigami-like architectures that can self-fold or different types of actuators that have shape memory properties that can even be useful for biomedical applications. So you can see here that polymer materials play a very important role, and it's not just dealing with commodity plastics such as PLA or ABS, which is very common for 3D printing, but we can rely on, let's say, plastics that are high performance like PEEK, Ultem, PEI, or liquid crystalline polymers, which have a very special space in terms of even metal replacement. And here you can see that the comparison between a thermoplastic and a thermoset can be done both on a cost and performance basis. So in fact, the 3D printing of rubber or different thermoset and thermoplastic elastomers is something that we focus, our group in particular, to join this space of thermoplastics, thermosets, and elastomers. So the possibilities here are very high. Many industries will take advantage of this and are taking advantage of this now, whether it's in rapid prototyping or in limited production, or the use of different materials that can replace metals or ceramics. And therefore, the material space and the 3D printing design is very big. I mean, if you look at this is a Jeep. When was the last production of this World War II Jeep? It was made during World War II at the war effort. And probably the last real production was done in the 1940s or 50s. So it's no longer produced, but because of 3D printing, and this was done at Oak Ridge, we were able to look at the possibility of producing this. And I think this was done even less than 6 months, where almost 70% of this composition of this big Jeep was done by 3D printing. So you can imagine the windshield, the lights, the rubber were not 3D printed. So where does 3D printing lie in terms of manufacturing? Wherever you can combine complexity and high performance, that's where 3D printing shines. It's very hard to compete with traditional manufacturing or formative manufacturing, such as injection molding, thermoforming, but where you can produce complex shapes, properties, high performance, 3D printing is always a winner. So where did we focus in the material space? So looking at the ability to control properties with a very small amount of additive, this is in the area of nanocomposites. So it's very well known that if you add anything less than 1%, nanomaterials are viable as commercial additives. And you don't need much, maybe about 2%, 5% at the most, but anywhere you can do 0.1%, you can improve the thermomechanical properties, the barrier properties, introduce new types of stimuli response, even sensing. So many of the commercially available materials today, including carbon nanotubes, graphene, nanoclay, silica particles, are fair game. So in fact, when we started work in 3D printing, we focused on nanocomposites. So for example, you can look at the addition of graphene on polyurethane, or nanoclay on elastomeric TPU, or different types of graphene using SLA, FDM, VSP. I'm not going to define all of this, but where you see these acronyms, they are referring to specific 3D printing techniques. And so we've been busy trying to develop new types of nanomaterial composites that allow us to observe very high changes in the property and function. Actually, my first introduction to 3D printing goes back to 1997. I did not realize back then it was already 3D printing. You see these structures here with very fine and high resolution, up to 100 nanometer level these days, was actually done using lithography. It's called stereolithography. It is related to the SLA technique, except that this was done with 2-photon efficiency. So the 2-photon resonance efficiency allows one to get very high voxelization or resolution, and they're quite expensive as instruments. I mean, you can probably spend about 400, 500,000, but you can see the possibilities of using micro machines, nano MEMS devices using this procedure. So for example, if we go to the family of SLA and DLP, which stands for stereolithographic apparatus, or DLP, which stands for digital light processing, this is basically done with 1-photon polymerization, meaning the traditional reaction of initiation, propagation, and termination that's driven by the initiator, radical initiator. So this can be done by stereolithographic apparatus or the print technique, which was patented a while ago, led by Carbon as a company. And then you can see here the big difference. So they give very high resolution, almost indistinguishable to injection molded plastic. But they're actually thermosets, okay, or thermoset elastomers, because they're driven by cross-linking of the acrylate resins. And so you can see here how it is done. Sometimes we call this vat polymerization, where the resin composition is part of a vat container. And then where you have the laser light guided or even projection coming from light driven by mirrors will allow the photopolymerization to occur and eventually the development of this object. And we've done some work on this. I'm just going to show one example. So for example, you can take coconut or abaca, and then you isolate the fibrils, the nanocellulose eventually derived from these fibrils. So you can see the crystallinity is very important, but these are really lignocellulosic sources. And you can imagine here, agave, your tequila source is a good starting material, okay? So if we break this down, you can end up with these nano whiskers or nanocellulose. All we need to do is add them on the resin at various compositions and we can 3D print them. So in this case, we mix the nanocellulose with polyethylene glycol diacrylate together with diluent monomers and initiators, and then finally 3D print them. And as you can see, the interesting properties can be demonstrated easily by doing what we call the percolation theory, meaning depending on the composition, you can see the changes in the property. And this particular example, we only added 0.31 weight percent, very little. And it doubled the tensile strength, it doubled the elongation percentage, and it almost quadrupled the fraction energy. What does that tell you? There's a lot of room for nanomaterial in 3D printing in improving properties. And this is a common theme that I want you to look at in each of the examples that I'll show you. And so you can see here, based on DMA, we can get the glass transition temperature, the tensile values, the swelling behavior, and then finally demonstrated the 3D printing of an artificial ear that you can use for implants. Now, a problem with another technique called FDM is with fused deposition modeling, you're basically extruding plastic melt. And what happens is based on the thermal history, based on the melting point, the glass transition temperature, or really the quenching properties, you can have defects based on this void space. But yet, this is one of the most important 3D printing method because this was used to 3D print that Jeep. It was used to 3D print that sports car. So trying to improve and solve this is one of the things that we have done in our group. And I'm not going to belabor some of that. But really, the majority of the examples I'll show you is based on extrusion printing called direct ink writing, okay? So anyway, one example we did with the FDM was we mixed the thermoplastic polyurethane with nanoclay. The TPU is basically a polymer with a hard and soft segment that allows us to control the properties, the elastomeric or rubbery properties based on the chemistry of your polyisocyanate, your isocyanate and your polyol combinations. So together with graphene oxide, we introduced this to TPU with some plasticizers and a compatibilizing PLA. And of course, we monitor the composition based on the Raman spectra, the D and G band, and then finally demonstrated filaments that we can feed the FDM printer. And here are some of the prints. You can see that we were able to retain the elastomeric properties. But how good are they in terms of their thermomechanical properties? So you can almost distinguish here direction based on the parallel or perpendicular to the build plate. And indeed, those two directions can have different properties because of the orientation and the anisotropy of the flow. So for example, with compression modulus, it's almost a linear increase with increasing graphene oxide, as you can see here, on both the parallel and perpendicular printing direction. And here are the row L and S compression curves. On the other hand, when we look at the tensile modulus, we did not see a linear behavior, but rather an almost doubling of the tensile modulus with as little as 0.5 weight%. What that means is that we don't have to add more. We don't have to add 1, 2, 3. 0.5 is enough to almost double the tensile modulus. It's because the nanostructuring, the deaggregation, the homogenization of the nanomaterial is a very important practice that we have done and use that as a guide to optimization of the property. And as you can see here, this TPU and the graphene oxide are biocompatible because of the high survivability of osteoblasts and fibroblast cells using this cell viability experiment. Now, what happens when we take that plastic polyurethane and we change the design? Let's say we introduce a design that is very porous. So from the 3D printing image, as you can see here, and the modeling, what if we also introduce a porosity that is based on microstructuring? And so if we do that, we would need a different printing method. This printing method is called DIW, direct ink writing, or sometimes we call this viscous solution printing, or sometimes we just call it ketchup printing. And what's important here is to pay particular attention to rheology, meaning a shear thinning behavior, sufficient yield stress greater than 200 pascals, and also sufficient storage modulus. So we load the material on a CNC movement printer. What you have here is the extrusion of the paste based on pneumatic or mechanical injection, and then the precise movement derives the shape and eventual curing behavior. And as you can see here, this is really how you 3D print cement. This is how you 3D print chocolate, okay? So you can see here that the viscous properties are very important. And as you can see here, a shear thinning requirement is one of the easiest characterization that can be made. But to optimize the printing, you have to look at the adhesion, the flow rate, as well as the different types of movement to optimize curing as well as flow behavior. And so to do this work, we actually took this plastic, the same plastic that we 3D printed by FDM. We had to formulate one that contains nanoclay, and I'll explain to you why we did that, some silica particles or rheological modifiers, as well as a plasticizer. So if we did that, we came up with the right rheology where the storage and loss modulus overlap. That's very important because that means the material will flow. And when you reverse or remove that stress, it will stay to its form. So the shear thinning behavior does change with composition. And then we were able to 3D print it with very high or very good resolution. Now the clay was removed, and this is very important, by treating it with hydrofluoric acid. Now the hydrofluoric acid is something you don't want to do, but we had to do it. And since then, we've used salts, and I'll explain to you a different experiment. But when you do that, you create a microporosity that looks like this. So this microporosity, depending on the clay content, and of course the swelling accompanying it, should result in various mechanical properties closer to an elastomer. I mean, we can plot this in terms of the density changes, in terms of the compression modulus, but it's better to see a movie. I think in this talk, you'll see several movies, okay? So let's see if I can have my pointer. Oops. I don't want to end the show, but we'll see if we can. There you go. Okay. I think I can get it from here. Thank you. So here you can see the plastic as it is printed. You press on it, very low yield, okay? Typical plastic. What if we change the size of the holes or the ridge, okay? So here you can see some deformation based on the large opening of the ridge, okay? So you can bend it, some hysteresis. But what if we remove the nanoclay and create the micropore structure on the same cube? If we do that, we will end up with a material that is very compressible. In fact, this is compressible up to 1,000 times with 60% retention. And my colleagues told me, oh, wow, that's a super rubber or super compression, okay? Or if you change the composition, of course, you will have a different elasticity as shown here. Here you can see a lot of hysteresis, but then we have less porous structure. So what this tells you is that you can use plastic to convert it into a foam. You can change some of the properties simply by changing the geometry without changing much about the covalent bonding. And here is the performance of that super rubber. Now, let's turn to another elastomer, and this time it's silicone. So silicone has many uses for industrial applications, OEMs, medical, etc. And it's based really on cross-linking information of the siloxane units. Very well-known chemistry, can involve the use of catalysts, but we can 3D print them. So how do we do this? Well, you can go to Home Depot. I think you have Home Depot here in Mexico, right? So if you like to work on your house because your house is old, you will buy this, you put it on your bathroom, and then it will dry, okay? So what we did is we took the same material and we put it on a printer. We either use the Hyrel printer engine or modified Ultimaker, just like what I showed you earlier, and then did some 3D printing. So the easiest work we can do is just change the size of the tip. From 0.6 to 0.1, you can see the dramatic change in resolution. And what if you ask me, well, can it make more complex shapes? Yeah, we can. We can make this vase, or if you play tennis, we can make a tennis ball for you. Probably you don't like this because as you hit it, it just falls flat. Absorbs a lot of the energy, okay? So things we can do with that. Now, it turns out when you go to Home Depot, you can have 40 different adhesives, sealants. Some are based on polyurethane, epoxy, acrylate, chemistry, SBR rubber, and it turns out we can 3D print most of them. So here are some of the things we printed on those various commercial DIY adhesives and sealants, and we even published 4 papers. Okay, so really, there's research in Home Depot. All right, so let's go back to serious things. So silicone materials. So I said earlier, we don't like to use HF, hydrofluoric acid. It's bad. It's going to kill my students. So I said, why don't we use salt, table salt? In that way, we can use water to clean them up. So indeed, we prepared another composition using salt microparticles, silicone oil, but at the same time, we use PDMS, the silicone, commercial silicone. And then we added silicone oil and we started printing. And as you can see here, we were able to make very nice prints. But before we ended up with this print, we of course studied the rheology, viscosity, and so on. So I can tell you a lot of the things we discovered with 3D printing, rheology. It's very important for you to master the art and science of rheology because that allows you to optimize the properties as well as the 3D printability of materials. And here you can see after we dissolve the table salt, we can get the same porosity almost as I've shown you earlier. And we can 3D print them and we can have the super compressibility, just like I showed you earlier with polyurethane, very high compression, different strain rates, okay? But what's interesting here is this. When we took this material, we dropped some water, the water did not penetrate it. And we just colored water blue so you can see that it produces a super hydrophobic effect. But what if we soak it in kerosene, cooking oil, okay, gasoline? It turns out that it loves it. It soaks, and we just colored the oil red, so you can see visually that this material, which was 3D printed, loves oil but hates water. Okay, and we can squeeze it up to 10 times with very little change in performance. So we can use this for oil spill cleanup, okay, or different types of emulsion breaking, okay. And as you can see here, we can even 3D print one which contains carbon nanotube or graphene, so we can have multi-material printing. And moreover, it is a super rubber. So you can see building up many different material properties and strategies to use it as practical devices or practical applications can be done by a combination of materials and 3D printing. I mean, again, let's go back to the same plastic, the TPU. What if we add carbon black? Carbon black is very common. It's used in the rubber industry to make the rubber colored black, you know, the tire. So we used the carbon black and we made various compositions in order to look at the percolation where we change the resistance or conductivity, and then we can use this type of percolation to sense or monitor motion or movement. Now, I can tell you this was not an easy project or the rest of the project. It took 6 months to a year, sometimes a year and a half to get the right formulation. It's because we did not use AI, okay, and machine learning. And I'll explain to you an example or several examples why this is so important. So it took us 1 year. That means I paid a postdoc 1 year. That's about $60,000. Maybe I paid too much, okay? What if I have a way to get a project done, 3 months, maybe I only pay, $20,000 or $10,000 for the time of the postdoc. So I can have 6 papers in one postdoc, right? So that's the math. And anyway, as you can see here, it took us some time to get the formulation right. Finally, we get the right formulation. We 3D printed it, and then we came up with the right composition. We put it in a pad. We put it under the shoes, and then we started walking, jumping, bending our knee, and you can see here different types of movement made us a very robust strain sensor. And this is all by 3D printing with an optimized material that is capable of sensing based on change in resistance with movement. Another example is based on the FDM printing. This FDM printing made use of a composition of epoxy and benzoxazine. When we combine it with carbon nanotubes, it prints very well. And then finally, you can see here, this is another movie where you can see a smooth 3D printing process. We can get high resolution. The color is black because of the carbon nanotube. And then when we characterize this cross-linking of the epoxy group and the benzoxazine, a thermoset, the benzoxazine required curing at 200 degrees Celsius. So these are very strong, high temperature stable thermosets. We did the mechanical testing and we demonstrated the folding as well as the shape memory and then very isotropic structure. By the way, how much time do I still have, Jose? Oh, the low battery. Yeah, I have a yeah, computer is okay, but if I have a low battery, we're bad. Okay. All right, thank you. Thank you. So anyway, so demonstrating here that we can have shape memory material, again, a movie. So you can see here, after we've changed the shape by heating, we can cool it to restore it to the original shape. and we can go it back and forth, back and forth. So the hysteresis and the retention of the shape follows the temperature and the restoration time. So this is, again, a type of 4D printing, okay? So probably almost on the last leg of 3D printing, and then an introduction on synthesis using machine learning, and then we're done, okay? So where does AI come in? AI, machine learning, digital manufacturing, simulation. This is the hot topic, if you would say, but I can tell you that you have to learn it. The reason is if you don't, in 5 years or maybe 10 years, you will have no job, okay? Because AI and machine learning is a tool, sometimes very much the same as we started using a computer or a slide rule and a calculator. It will be employed in many things we do, from design of experiment to characterization to different types of new or de novo synthesis design. You see, AI has a subset. It's called machine learning. And actually, you have been doing machine learning. You don't realize that. It came in the form of design of experiment, statistics. Sometimes we call it the Taguchi method, okay? So all this optimization, principal component analysis, allows you to shorten your work time by focusing on the most important variables. And then sometimes when you develop complex algorithms, you have to generate new neural network compositions or GNNs, and then you can come up with a better algorithm and again use that for learning, okay? So the deep learning, it's not really just only deep fake, is when you try to deconstruct or come up with more creative ways to do the experiment. Now, AI relies a lot on what we call digital twins. The digital twins is related to how we do simulation. So as chemists, you start from atomistic or quantum chemistry. And then as engineers, you end up with unit operation. Or as a mechanical engineer, you will do finite element analysis. So from atomistic to coarse grain to self-consistent field theory to finite element analysis, multiphysics, all the way to reaction engineer optimization, they're all part of what we call the digital twin. The more you do this, the more you will save time. Another way to generate artificial data or ideal data. And then when you team up with an experimentalist or somebody who actually works in the lab, you will have a very potent team because you will have the digital twin to guide you in your work, and you have the resource to actually prove what was predicted. And if you have a good loop between the digital twin and the experimental station, you will have what we call autonomous learning. That's scary because when this combination is taken together, that will replace you. Okay, but I'm here to say probably that will be not in the next 5 or 10 years because the human in the loop we're finding out is very, very important. Okay, the human in the loop or the scientist in the loop. And so you can have the digital twins basically as another field or subset in AI. Now, where I come into machine learning is developing workflows. And I can tell you what made me look at this more closely, and probably most of our experiments in the future will be done this way. You see, in machine learning, you start with a training data set of a data. Now, that data can come from what we call large language models. These are really what is in ChatGPT or in Google, okay? It's really a survey of all the data and the relationships done so far. So LLMs or large language models are fundamental to building that strong database. On the other hand, that data can also come from your own experiments or from literature data. And then in starting an experiment or workflow, you take a subset of this data and you call that your initial training data set. That training data set can be governed by an algorithm, basically an equation that allows you to predict a property you want or to guide you on the optimization path. And then you need to develop an evaluation protocol where you train your data, you plug into your algorithm, you actually do the experiment, right? And then you have an evaluation or monitoring based on a sensor. You feed that data or results generated in this testing data set, and you develop a feedback loop mechanism. Now, when you have that type of mechanism, a circular feedback loop mechanism, we call that real-time machine learning. So the more you do this, the more you will perfect the model, the more you will optimize the processing or science. And therefore, the workflow based on this type of combination and scheme is what will lead to shorter experiments and maybe better discovery modes. In fact, it can go all the way to production and different types of manufacturing, where other than the work you've done experimentally, you apply that towards optimization of processes, supply chain, variables that you have outside, or you don't have control what's on the outside, but if you plug in those uncertainties, that can come up with the ultimate workflow that governs your operation. And this is the story. So I told you the projects, we took us 1 year, 1.5 years. I spent a lot of money, okay, for the students. What if we have a project that we can do in 3 months? This is the project. So teaming up with colleagues at the University of North Texas, we observed that PVDF, a piezoelectric material, can be 3D printed, and we can have a quadrupling of the piezoelectric effect simply by 3D printing it. What if we can add MXene particles like molybdenum sulfide, vanadium oxide, molybdenum selenide, and we can have various compositions? We found that the effect was dramatic on the beta phase, meaning the crystallinity of the piezoelectric behavior, which was governed by the beta phase. And then we observed that by IR, Raman, and other spectroscopic techniques. But did we do this unilaterally with the experiment itself? No, we did a lot of modeling. This was done by finite element analysis with abacus learning. So we started with various compositions. We tried to predict the orientation, the nanostructuring, the rheology, and then finally came out with simpler methods of monitoring the reaction. And then finally, we were able to gather all this data, complete the characterization, and all of this was done in 3 months. Okay? So this is how powerful when you use the tools of machine learning on a project. And you can really come up with very interesting properties. In this case, a record 4 times increase in the piezoelectric behavior with PVDF by the incorporation of your MXene. Now, this is really my last part of the talk. What if we carry further machine learning to the actual synthesis of the material? At Oak Ridge National Lab, we have a group, and I lead this in the experimental regime, where we employ digital twins, we employ simulation, we look at the use of the flow chemistry synthesis methodology, Python programming, and different types of field modifications to control the optimization of the reaction. So actually, we have been doing a lot of flow chemistry in our lab. The reaction, instead of doing it in a flask, you do it in a flow reactor, meaning you do it in a column, a plug flow, a time series or space series reaction, where you can control the pressure, the volume, the temperature, the flow rate, the composition, much like you would do with a big chemical plant or a pilot reactor, except that this thing fits in a bench about this. So I call this my mini factory or my mini reactor. And really, this can produce you kilos of material if you let it run 24/7, okay? You don't have to work up, you don't have to, if you do the optimization, you have continuous production. Anyway, the workflow here can be done with that reactor. We can try to predict some of the initial properties, maybe develop large language models in the future with regards to sequence reactions or polymerization, and even employ outside help from a powerful computer. By the way, Oak Ridge National Lab has the world record of the fastest computer. It's called the frontier, okay? And that computational facility is also available for us. So if we do this algorithm and employ it on reaction synthesis, we can have various polymers, let's say, we can use for carbon capture or synthesis of vitramers or recycling. Now, to give you a scheme of this, we have a reactor. We develop several interfaces or APIs on instruments. These instruments are essentially monitoring instruments. We have an operating system that can be housed on an edge computer. That, in turn, will have an operating system that controls both the reactor and also monitors what is going on using online or in situ measurements. And in fact, a simpler scheme should look like this. So if we have this flow reactor right here, we can dose it, control the pump with the pump, the flow rate, and here controlling the temperature, the pressure, the flow rate. And we have to build several analytical instruments that can be part of the online monitoring in a time series. We can do a two-dimensional plot. We can monitor the IR, the Raman, the evolution of free radicals. Everything is part of a computer that controls and monitors the reaction. So to do that, you need several instruments, or maybe even just one, that can be connected to the flow reactor, which then reports to the computer that allows us to do real-time machine learning based on the feedback and control of the dosing and parameters, along with the known algorithms that we can shift based on the spectral data, for example, that we gather. And so this edge computer is very important because everything can be done inside the room, but if we need more help, or even if we want to control the instrument remotely, we can do that, or even access a high computing facility that allows us to do this reaction in real-time algorithm development. So to do this, of course, we need to develop this ecosystem where we have our own operating system. A lot of these modular monitoring stations actually has to be interfaced with the reactor, but we've been finding that we can actually make our own instruments. And these instruments, once you hook it up to your flow reactor, allows you to monitor the reaction kinetics, the mechanism based on specific algorithms or even theory. So we demonstrated this, or have been demonstrating basically with polymerization. What if we can control the copolymerization of 2 or 3 monomers in a reactor where we can optimize the temperature, the flow rate, the pressure, and then come up with a training data with a correlation that we can look at the success of that monitoring. So just to give you a picture, our objective, if we do the Bayesian approach of Synton, meaning we deconstruct the problem or reduction of the problem. So if our objective is to come up with an optically grade 3D printed contact lens, so that means we need to come up with the material. How do we come up with the material? We have to come up with a sequence. And then we can try to monitor that reaction by looking at, let's say, a time series of the NMR, the UV-Vis, as the reaction goes on with various combinations. So if you do this, you will end up with essentially real-time machine learning. And we've been busy. We've been trying to report some of these combinations or possibilities. Right now, we have a project related to copolymerization, control of sequence, and gradients. And so I have shown you in many ways how AI and machine learning can help you. How AI and machine learning has to be tools that you can use in your enterprise and at least to prevent you from being jobless. And finally, of course, muchas gracias. And I'd like to thank Jose and Tanya for hosting us, and of course, long-term friendship, and hopefully we can do more things together. Gracias.
Hey, thank you, Rigoberto. Very nice, always, presentation. Thank you, thank you. We have time for questions. First, you have questions from the other Synapses campus? Okay. We have time question for here, for the local
Sí, hay una en
audience.
Chihuahua.
We have one in Chihuahua. Go ahead.
I just want to know surface area of de las cosas que presentó de los cubitos, of the small pieces, the cube pieces. When you say that you remove the clay, which the surface area of this?
Very good question. We did not measure the surface area directly with, let's say, BTS or other types of surface measurement experiments. However, what we were able to empirically demonstrate is you can change the porosity size. And we obtained that data by SEM. So indeed, the larger the pore size, the more flexible the material. However, if we have more closed cell structures, eventually that's lower surface area because of the poor penetration of the mobile media, if you're using that. We will have a lower surface area and we observe poor compressibility. So quantification of that surface area or absorption is very important.
¿Se puede otra?
Other question? Yeah. Okay. Yeah, in Chihuahua, there are questions.
Y un momentito.
Thanks for your lecture. Do you think in some moment 3D printing replace molding injection?
Okay. So at this point, I would say no. Injection molding is a very important formative manufacturing method because you can produce millions on one mold. And still, you can, and it's being used for mass production. On the other hand, for limited production and high complexity or high performance, 3D printing or even 4D printing will be more useful and important. So actually, you can divide manufacturing into three types. You have the formative manufacturing, which includes your injection molding, your thermoforming, rotation molding, etc. You have your subtractive manufacturing, which is a form of milling, machining. And then lastly, you have additive manufacturing, to which 3D printing comes. And I would say you will need all three of them. All three of them have very important uses and value chain. So I don't think it will replace formative manufacturing per se, but you can use all three of them in what we call hybrid manufacturing to complete the project. And more, I see projects being done that way, where they combine the three types of manufacturing together.
Okay, we have other question, Chihuahua.
Yes, we have another one.
Okay, go ahead.
Thank you very much, Professor Advincula, for your presentation. It was really
¿Podrían hablar un poco más fuerte, por favor? ¿No se escucha?
Yes, thank you very much for your presentation, Professor Advincula. It was really interesting to see how was the evolution of your research during more or less 20 years. And I would like to know which have been the most important challenges that you have faced during all these transitions from the polymer chemistry to the 3D printing, and now to the artificial intelligence and machine learning? And also, how possible is that could be that some of our students from the polymer groups here in Chihuahua could be visiting you in some of your laboratories, and also some of the researchers, if there is the possibility to take some internships or postdoc or sabbatical stays.
What's the most difficult challenge you face in the chemistry or yeah, no, I like those questions. Really gives you an overview of how we approach things. So I can tell you my background is chemistry. I'm not a engineer by professional training or education training, but most of my students today are engineers. In fact, I don't have a chemistry student right now, which I'm crying, okay? Because I need more chemists. So I have students from electrical engineering, mechanical engineering, biomedical engineering, chemical engineering. They want to work in my lab. So I have to give them something that does not involve chemistry. Okay. But they're very good in making the 3D printer work, optimizing the 3D printing, applying machine learning, doing interfacing, even making new instruments for me. So I love that aspect. So in that case, my work in that area or effort in that area is easier these days. But in the past, as I said, and I showed you, my background is in synthesizing different types of polymer microstructure. Imagine if I can keep my lab where I have a very strong synthesis, formulation, compounding, 3D printing, and then now a team doing simulation and machine learning. So if you have this, and by the way, I have the national lab of fridge probably to help me. You can do a lot of things. So yes, that question is really dependent on the skills, the opportunities, and the facilities available.
Okay, thank you. If other question in Chihuahua?
Yes,
If not, we open the question here, the unit.
yes.
Thank you, Professor Advincula, for your presentation. I'd like to know how possible is to evaluate the
Okay,
pollution.
¿podrían apagar el micrófono en las otras subsedes, por favor?
The
Están
pollution
haciendo otra pregunta, perdón.
Okay.
Es que, ¿puedes hablar más fuerte? Es que no se escucha realmente.
I was asking you about the possible consequences of producing microplastics in 3D printing and the consequences in the future for being used as for human consumption or packaging. How can we evaluate this at this point, or is it still not considered?
Good question, valid question. Probably you have a lot of microplastics already in your body. Same with me. Yes, so how can we reduce it? Good news is we can probably make a dent in reducing microplastics using 3D printing. You see, 3D printing is additive. Additive means we only use the material we need to make or manufacture the object. In injection molding, you have wasted parts or the bearing. In subtractive manufacturing, you have even more waste because you have to cut, mill, subtract, and throw away the waste plastic. But in additive manufacturing, since everything is done by adding layers or using only the amount you have, you can use less plastic. And maybe that's an indirect answer to microplastics. And again, by the way, microplastics is here to stay. We can be either alarmed with it or we can just accept it as a fact. Another threat is called the PFAS, which is anything that's related to fluorinated polymers. And fluorinated polymers have been with us for more than 50 years. But the problem is, what is the problem? Okay. So again, microplastics is here to stay. That's my opinion. We just need to accept it, understand, and probably all of us have microplastics anyway.
Thank you, Rigoberto. We want the opportunity to make questions here in Monterrey, please.
It's about the 3D challenges. Like in your opinion, what are the currently 3D challenges that need to work?
The main or big ones.
Yeah.
Yeah. Okay. Yeah. So in 3D printing, one of the complaints is the cost. The cost can be expensive if you are producing a part that can be done by formative manufacturing. So again, the key is find an application that will give you a huge savings in cost and time. Okay. So that is one of the challenge. The other is, of course, materials. So even though I've shown you a lot of materials research, the materials challenge is how to reduce the amount of what we call residual stress in printing. Meaning when you do this printing, this is not the same as injection molding or monolith. You're actually introducing defects each time you print a layer because you're quenching or you have a poor distribution of your material and so on. So that is a challenge, how to minimize the residual stress so that it is compatible with current ASTM ISO standards of properties. Okay, and probably for me, the third is manpower. We don't have enough people doing 3D printing to really engage in optimization and to be hired by many companies to demonstrate the power of 3D printing. So I think it's an opportunity actually that many people should look at 3D printing as a part of their curriculum or training.
Any other question?
Jose?
Manuel.
Thank you, Professor. I really impressed every time I see your presentation. Very topic. For the main goal for absorption oil, I think petroleum for the water. What did you think? What's the main problem take when you uptake this oil?
Mm-hmm.
So there is a process for desorbent these materials?
Yeah, so in that demonstration, we basically use silicone oil as part of the formulation. So as you know, silicone hates water. And because of that formulation, we instantly have a dichotomy of absorption, physical absorption properties. The other thing is we were able to use the porous nature of the material to do the soaking of oil. So there's a lot of internal volume that's still capable of containing or storing that oil. So really, that we have a movie where after soaking, you can use your gloves and squeeze the oil out and do it again 10 times. And that means basically this is a foam that is able to recover oil or even break emulsions. I would not use it for cleaning. It's too expensive for cleaning, okay? But this is a very interesting way of oil recovery or capture. Yeah.
Really interesting. Just a second one. For the particle size that you use for the salt, for, make porosity, you have control for the particle size using that or?
So we tried to buy the finest salt we can get. I think we tried to also use some grinding to get it even finer. So it's as small as you can get and then incorporate it in the formulation. So yeah, you can buy some micro particles of salts.
Thank you very much.
We have another question.
Thank you very much, Professor, for your amazing talk. I'm very glad to hear it. I have several questions, but I will only make two if possible. The first one is, I didn't understood very much the purpose of the carbon nanomaterials on your composites. What is that about? Just mechanical properties, the change of mechanical properties, or is there anything else?
Mhm. So probably you're referring to the strain sensor we developed with the carbon black.
No, I'm talking about when you use the graphene and the
Okay.
carbon nanotubes with acrylate.
Good question. So the carbon nanotube is actually, of course, it's a spaghetti noodle. It has an entanglement, and for the most part, it helps us modify the viscosity, made it thicker. But then we also have a corresponding increase in thermal and electrical conductivity. Now, the graphene has a different mechanism. The graphene basically allows us to distribute the graphene platelets and enable more surface contact. Depending on the hydrophilicity, the compatibilization with graphene is easier. And again, we have the corresponding increase in thermal and electrical conductivity. But we have a project now, we actually combine both. And we got very good percolation with very small amounts of both, with excellent electrical thermal conductivity and high control of the rheology.
Okay, thank you very much. And the second one is going to be about this whole system you have developed with the machine learning. You were talking about making the polymers and have all these spectroscopic systems. It wasn't very clear for me if you have like continuous flow measurement mode, or you have to manually take the sample and go to each spectroscopic apparatus to make the measurements, or how does it works?
Yes. So the base unit was the continuous flow reactor. So yes, it's a continuous flow. We define the flow rate based on the pumps we use, and then we can control the pressure, the temperature, the feed ratio of the components. So everything is flowing, just like doing a reaction in a pipe, okay? Or HPLC, okay? And then the monitoring instrument is attached to the flow, meaning we have optical sensors or flow cells that can monitor the chemical shift by NMR or Raman or IR or refractive index. So we do what we call a time series. Time series is simply you monitor the spectra every 3 minutes, every 30 seconds. So you do this time series, you collect them, and then you see the evolution of the spectra with respect to the flow rate or the reaction kinetics. So this is all relational, and we did not do this blinded. We targeted specific time series. In fact, we can do what we call space series. Space series is when you modulate the flow with a plug flow system, and you can have a multi-phase reaction where the reaction is enclosed in an oil. So, and then we have various types, packed bed and everything. So really, there's a lot of reaction engineering possibilities. So the question is, with the online monitoring, we basically do what we call in situ monitoring or in operando measurements. With that, you get a real-time feedback that you can relate to the variables you change, the reaction ratio of your ingredients. And so with that feedback, you can develop a model of the kinetics and differentiate it from a batch reactor. So I think a good question here is, why did we choose a flow reactor base versus doing it in a flask? Well, in a flask, you have problems. When you heat it up, you have poor thermal distribution. You have to mix it, you have to reflux it to make it a closed system. And then finally, it takes you 1 week to complete the reaction with 5% yield. We have found with the flow reactor that we can get the product in minutes, we can get a high yield, and we can let the reaction go on for 7 days and collect 1 kilogram of the product. So I believe the future of organic chemistry and polymer chemistry lies eventually with more engineering on the science. If you're an organic chemist, you did not train for that. And I will advocate, if I go back to my teaching mode, I will advocate every organic chemist should learn flow reaction.
Thank you very much.
Okay, other question?
Thank you, Rigoberto, for your nice talk. I have a question for the people working on composites or nanocomposites materials. We're looking for an isotropic response of these materials. If we can move to the 3D printing area, what is your opinion about what is the best technique for have this isotropic response in composite and nanocomposite designs?
Yeah. So we have these different methods of 3D printing that I showed you. One is very directional, based on extrusion. Another is based on photopolymerization, which actually relies on rheology. But then you need to have very good distribution or mixing. So with nanocomposites, it's as good as your mixing method. And sometimes I tell my students, you need to develop the art of mixing. It's not science, but it's always try this, try that, use an ultra centrifugation, use your toothbrush, whatever will work. But then when you make that work, you stick to it. Don't change it in the middle of the game because you will have a different result.
Yeah.
And that's why it took a year, okay, to do these things. Now, with machine learning, we already know the target concentration. All we need to do is employ the best mixing method, the predicted viscosity, and actually a good tool for us is ultra centrifugation or centrifugal mixing or different types of mechanical methods with an impeller. But anything you can use to optimize the distribution of your nanomaterial will only help you determine the fastest way towards optimization. So I would say it's about mixing, 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 mixing.
Okay, other questions? Okay, we have two.
As an engineering undergrad student, how can I prepare myself for an industry that's going to be rely a lot on machine learning? Like,
Mhm.
what can I do to be more involved in that world?
Okay. Good question. Again, these are all very interesting questions. So I have 3 words: statistics, statistics, statistics. Okay. So start with a really good grasp of statistics, probability, etc. It's because it's the foundation of designing an experiment, or at least determining precision versus accuracy. Once you have that use and the orientation from statistics, it's easier to go towards algorithm development. The algorithm development borrows a lot from many things that we already know in design of experiments or principal component analysis, and then with simulation. So if you take the time to learn simulation, maybe some of you don't want statistics. Maybe you want multi-physics modeling, like COMSOL physics or finite element analysis. That is also a very useful tool because that gives you some digital twin development on the mechanical properties or heat transfer. So I would say, as an undergraduate student, and I keep telling this to my students, start learning some of these tools of the trade and make it a part of your skill set. I mean, Python programming. Everybody's doing Python, okay? Python programming. But I can tell you, Python programming, you will have many competition because even girls can do Python programming, okay? Little, I'm not belittling the skill, but this can go all the way to elementary school. But what you need to do is become an expert in your science domain. Meaning, if you're an organic chemist, be the best organic chemist in terms of your fundamental knowledge. If you're a mechanical engineer, understand the principles of mechanical properties and material properties. And then these tools on AI machine learning are just tools that you can learn after. Thank you very much.
Okay, the question?
Thanks for your talk. It's really a lot to absorb, but it's all very, very interesting.
Thank you.
Are there any efforts towards coupling these workflow systems, this synthesis towards the resin formulation or even to the printer?
Yes, yes. So the workflow here, so any of you doing formulating paints or different types of additives in plastics injection molding, as you know, each of these additive has a purpose, whether it's using to modify the viscosity or preventing oxidation or plasticizing. So each of these are well-known tricks or even part of your experience. The challenge is how to operationalize that knowledge and capture it in an algorithm. This is hard. This is hard. I can tell you earlier, I told you earlier, the human in the loop is not going to go away. So you're not going to be replaced yet, okay? But the more you document this loop of knowing the digital twin, the workflow, developing better algorithms, real-time machine learning, the more that experiential knowledge will be documented. And when you do that, 10 years, 20 years, yes, I'll be scared. I might be replaced by this automated laboratory or chemistry, okay? So in formulation, in different types of experiences, in compounding, still the human experience is very important, but one day this will become so good that it will start documenting all that experience.
It's all about feeding data.
Yes.
Okay.
So data, it's good you mentioned that because data is what they call the new oil. You know what I mean? Oil is very important for energy, and Mexico has a lot of oil, and it's an important resource, but data is going to be an important resource. So if Mexico has a way of collecting all that data or has a way of using data analytics to document what's unique about Mexican ecosystem, it's going to be very powerful. So you should invest on NVIDIA chips. Small tip.
Thank you.
Well, yeah. Last question for me. We start with the synthesis of different kind of polymers. We complex the synthesis to make a very high-performance polymers. And now we put this polymer now into the printers and different kind of. And then we use machine learning and also flow chemistry. What is the next step for the long vision for the future?
Yeah. So at this point, I would say AI machine learning is still getting more common, familiar. So I would say in the next 5 years, 10 years, there is still going to be an explosion of the laboratory onto the future based on AI and machine learning. And I cannot predict, let's say 5 years, 10 years from now. But as I told you, the more we integrate this, the more it might duplicate the human intelligence. In fact, there's what they call the Turing test. Have you heard of that? If you cannot distinguish the real thing from the fake thing, then it passes the Turing test. We have not yet reached that point, but if we reach that point, we have achieved something which can be good or bad, but we have achieved something. But right now, it is a tool, okay? And maybe like what I said about data, the more you can control data, document and curate data, the more you have ways of gathering data. And again, another scary thing, you know, there's already a lot of data on your iPhone that you don't know, or your Google, right? So, but data is the next big thing.
Thank you, Rigoberto, and thank you for your nice talk. Please, applause for Rigoberto for that. Now, I would like to invite the professor and Dr. Artisa Torres to give this recognition for you.
Yes, really a very, very great conference. I am really happy with this nice conference. On behalf of CIMAF, I think everyone say thank you very much. And I hope we can keep in touch and to strengthen all our links with you and all these two institutions. So I am very, very happy to deliver this diploma, this very modest diploma, but just like a kind of diploma to say thank you very much for this conference.
Thank you very much, Dr. Guerra. Yeah. Muchas gracias.
Gracias. Let's go because I have to move to Monterrey a las 3.